So we are supposed to find the energy eigenvalues and the corresponding energy eigncats. So one of the ways that people do this is write all of this in a matrix form. So this is the H11 component and so on. So based on this, one can write the given Hamiltonian in the form of a 2 by 2 matrix. There is 1 1, there is 2 2, there is 1 2, and there is 2 1. And one can easily determine the eigenvalues and everything from this, from the well-known formula of determinant of H minus lambda I is equals to 0. So this will give you all the eigenvalues, and from that you can calculate the eigenvectors as well. But we are not interested in writing the matrix. We want to do it without the matrix. So we want to use the algebra, the Dirac's bracket notation, all such things, without going into the matrix part. Okay, so first we have to find the eigenvalue. So how do we do that? Let's say the required state is some psi, and since this is an eigenvalue problem, let's say the eigenvalue is some E, and also they have asked that this psi is linear combination of these states, right? Linear combination of 1 and 2. Okay, so we just plug in the H that is given to us, and how do we go about it? So the first is 1 1 psi minus 2 psi plus psi this is equals to E psi. Say we define alpha as 1 psi and beta as 2 psi. So what do we get? We get this will become alpha 1 minus beta 2 plus beta 1 plus alpha 2. This is equals to E psi. Okay, so I can club all the 1 and 2's together, and let's see what happens. So is alpha plus beta, there is alpha minus beta is equals to E psi, and which is equals to E times alpha 1 plus E times beta 2. So if we compare the coefficients, what do we get? Is A times plus beta is equals to E alpha, and there is A times alpha minus beta is equals to E beta. Okay, yeah, so we have the energy eigenvalue E, and there is a relation between alpha and beta. So let's say we start with equation 1. Okay, what can we write? Okay, we have A alpha plus beta is equals to E alpha. That means alpha plus beta is equals to E alpha by A, and this implies that beta is equals to E alpha by A minus alpha, which is nothing but alpha by A E minus 1. Okay, so if we substitute this value of beta into equation 2, and what do we get? There is A minus beta, it is A minus 1 is equals to E times beta by A E minus 1. Okay, so okay, so there is A alpha minus alpha E plus alpha equals to E square alpha by A minus E alpha by A. Okay, so I think I made a mistake here. So there will be E by A, yeah, if I take alpha outside. So sorry for this. If I take alpha outside, it will be E by A minus 1, right? And if we plug this back into equation 2, there is A alpha plus beta A minus 1, which is equals to E times beta, which is E alpha A minus 1. Okay, seems fair. Okay, so this will give us A alpha minus alpha E minus alpha E plus E alpha is equals to E square alpha by A minus E alpha. This both term will cancel. square alpha upon a. This gives us this alpha will cancel, so e square is equals to 2a square plus b is equals to plus or minus 2a. So these are the two eigenvalues. Okay, fine. So e1 is root 2a, so is minus 2a. Okay, so next we need to find eigencats. Let's say we start with this energy eigenvalue. So if we substitute the value of E here, what do we get? Then we will get beta is equals to alpha is root 2a by a minus 1. Okay. So this gives us alpha times 2 minus 1. Okay, so we have beta is equals to root 2 minus 1 times alpha. So we can always make a choice now that we can freely choose alpha and fix beta, or we can choose beta randomly and fix alpha, whatever is easy. So for simplicity we can choose, say, alpha is equals to 1. So that makes beta as just root 2 minus 1. So what was, let's say I name it the first eigenstate. It was alpha times 1 plus beta times 2. So we have fixed alpha to 1, beta is our root 2 minus 1 is 2. So did we find the eigencats? Well, not precisely, because we would like this square to be 1 for probability conservation. That would be normalized states. So if we look at this sum, it is not 1. So in order to find that, this is the normalized state condition, and that would give us the normalization would be what it would be when you do root 2 minus 1 whole square is equals to 1, 1 square is equals to 1 over this 3 minus 2 root 2. That's it. Yeah. Oh no, sorry. So plus 1 mod n square first 1 1 plus 2 minus 1 whole square is equals to 1. That is 1 plus 2 plus 1 minus 2 is equals to 1. So that would give me mod n square 4 minus 2 is equals to 1. That would give us mod n square is equals to 4 minus 2 root 2. Considering n to be purely real, we say this is 4 minus 2 root 2, so power 1 by 2, right? So we need to divide our state. Let's say this is now the normalized state with this 1 over n, so that is 1 plus root 2 minus 1 2 divided by 4 minus 2 root 2, this, right? So this is the eigenstate or eigencat v1 is equals to 2a, right? Similarly, we can just do it for the other state, and only the signs will change. Which signs? This negative will become positive, this positive will become negative. So 1 minus root 2 plus 1, as this sign will also change. Plus 2, right? Right, so we found the energy eigenvalues and we find the relevant eigencats.